I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
All right, hello and welcome to the Materialism Podcast, an exploration of the past, present, and future of material science. My name is Taylor Sparks, and I'm your host. Joining with me is Andrew Falkowski. Andrew, how you doing?
Doing pretty well. It's been a busy morning, but I'm glad to be here recording it. And we're also joined by Jason Sebastian of QuesTek. Jason, would you like to introduce yourself?
Hi, guys. Thanks. It's a pleasure to be here. I'm Jason Sebastian of QuesTek. I've been with QuesTek Innovations, which is a company in Evanston, Illinois, for about 18 years. Currently the company president. I'm involved in all sorts of things, from soup to nuts at the company, technical to governance to management. But we are a company that does integrated computational materials engineering and design. And I'm here to talk about some of the history of that and the current status of that. And again, thanks, guys. Pleasure to be here.
Hey, man, it's not every day we get the president of the company. Thanks for taking a minute. That's pretty exciting. Hey, I was just looking at your CV, and I couldn't help but I got to ask, you did a double degree in ceramic engineering and philosophy. Good for you, man. Tell me about that.
I did. It was at University of Illinois. I'm from Chicago, and I started college a year young. So this idea of 5 years doing 2 degrees was not crazy. And philosophy intrigued me. Of course, I was searching for the answers of all the secrets of life and the meaning of life. But no. It was fascinating. It got me exposed in general to liberal arts education, made me a better writer and communicator. I even got into some like high level logic classes that get borderline mathematics. No, but other than that, I hardly remember most of it. And I'm a material scientist, but ceramic engineering does not exist, as a specific degree anymore at Illinois. I was the last breed of ceramic engineer. It's now material science.
Yeah.
But I moved into metallurgy, mainly stuff and characterization in graduate school, and that's where I've been focused at QuesTek.
Okay. Well, today we've got a super cool episode. Why are we talking with the president of QuesTek? Well, there has been a fascinating evolution of materials and in all areas, but one of the really interesting case studies where we've seen it evolve dramatically over the last 100 years is in aviation. In aviation materials, we've gone from wood to very, very advanced materials. And the process of that will probably honestly be the future of a future episode, will be the subject of a future episode. But for today, we do want to talk with Jason, who's going to tell us about the most recent tools that are happening right now. To get us started, you want to tell us a little bit about a brief history of aviation materials, Jason?
Yeah, well, we'll finish here on some of the QuesTek examples, some of the exciting new examples of alloy design and alloy concurrency. But we were talking about the history, right? Originally, metallurgy as a whole was kind of an empirical, almost accidental science. You go back to the Wright brothers, right? That's where aviation starts. They had some constraints on how heavy the airplane could be, or the engine, in fact, and how many horsepower it had to put out, and it led them to the use of aluminum alloys. And they knew these aluminum alloys, these aluminum copper alloys, could get very strong, much stronger than regular aluminum. It was they did not discover these alloys, but the people that did sort of like accidentally stumbled upon them, and everybody got excited and utilized them. This moved to sort of an empirical age, and sort of empirical / accidental discovery age. We were talking a little bit a minute ago, but like the example of nitinol, this shape memory alloy that material scientists know and love. This was sort of an accidental discovery at the Naval Ordnance Lab. That's where it gets its name, Nickel Titanium Naval Ordnance Lab. This person, I think Bueller was his name. I'm not sure if it's the Bueller of metallography fame, but he was studying these alloys for their room temperature properties. He noticed as he was melting things around equiatomic titanium, nickel, he was like moving something out of the furnace. It hit the ground and made a thud. But if he moved something out of the furnace and water quenched it and then dropped it on the ground, it rang like a bell. told him there was some crystal structure thing happening, dampening effect at high temperatures. And he was like, wow, that's interesting. Somebody made it into a wire and bent up the wire and then blew their pipe smoke onto it. This is literally what I was reading. And the wire straightened
wild,
back out to its original form. So this was like another like accidental discovery. But then they eventually kind of understood, oh, this is a martensite-austenite transformation. This is a shape memory effect. But the original discovery was this sort of accidental thing. I've been told the example of titanium 6-4, it's an excellent alloy. It does the job. It may not be optimal. These integer numbers are often not. But I was told it came out of an empirical development program. It was motivated by the SR-71 Blackbird, the big supersonic plane in the 1950s and 60s, and they only had enough money to test the even numbers. I don't know if that's true or not.
Oh my gosh.
2's 4, 6, 8, and we'll never know if Ti 1, 3 was in fact the optimal solution. No, but it was something like that. It was an empirical program looking at compositions. And I think even niobium C103, which was the kind of a rocket nozzle material that came out of the Apollo program or the Saturn V program, this was like the 103rd test alloy in a sequence, right? So this is all very empirical. Yeah, I think it is. Maybe not all 103 of them, but it was like the 103rd designated.
Sure, yeah.
It's like something like that. But things have worked, right? And aviation has proceeded. Even the initial aluminum copper alloys, those have evolved into all the different classes, 5,000, 7,000, 6,000 series aerospace. I think it all started kind of with aluminum copper in terms of the higher strength, but it's kind of proceeded to where it is today. And that leads to the modern era, right? This proceeds, but it doesn't proceed, like you said, fast enough. And the need for new materials now and the need for new materials, more rapidly is greater than ever. And that's what's led to this current age of computational modeling, computational materials design. And it used to be called that, hey, computational materials modeling or materials design. It wasn't until about 14, 15, oh gosh, maybe almost 20 years ago now that the acronym ICME was developed. I think it was in a 2008 National Academy report. But QuesTek was around before that. So we were doing computational materials design. Materials by design is one of our trademarks. And then this field of ICME has come along. So we can talk about that and what that's all about, Taylor. But that was my quick kind of history. What's led to any one of those could be a full episode. We were talking about this, the history of aerospace aluminum, right? The history of nitinol. I'd love to understand that a little better.
Yeah, check out episode 9. We did a whole thing on nitinol. Oh,
really? Yeah. The funny thing about that was something in the original empirical melting of alloy sequences. This was quoting this guy, Bueller. Like, my first wife and I separated. I spent a tremendous amount of time working in the lab. So it was really because the guy had a lot of time on his hands that he was going through this empirical sequence of nickel titanium alloys. But anyway, no, I did not listen. I'll look up episode 9. Thank you.
Yeah, you bet.
Yeah. Listening to you going over this brief history, it really sounds like in many cases we sort of got lucky, and the dominant paradigm was really kind of like what Edison talked about, where it's 1% inspiration and 99% perspiration.
Yeah.
Where just trying things over and over again, and having at least the need to maybe direct those efforts, but not necessarily those efforts being the most efficient. And so, as material scientists, we want to know how can we actually tune all of these different parameters in our materials. How can we take advantage of the physics we understand to make the materials we want, but hopefully maybe faster and in a more targeted way? And that's where ICME really, I think, came on the stage and really allowed us with greater fidelity than ever before to actually start to design alloys and design materials. So maybe you can tell us a little about QuesTek and maybe your experience in using some of these tools to start to design materials. And what is involved in the ICME process? Is it analytical models? Is it CalFAD? Or is it even broader than that?
It is broader. It is those things, but broader. So QuesTek was formed out of the research of Greg Olson. He was one of the co-founders from Northwestern. He was historically kind of a steel martensite expert, but he was looking at all scales of alloy modeling, and even the martensite and steel experience led him to thermodynamics and CalFAD. For QuesTek, that's kind of the foundation of how ICME works. You're calculating the process, structure, property relationships in a material. So this is not just QuesTek. This is ICME. It's linking the process, structure, property, and performance relationships in the middle of a material. And the process structure, what temperature do you process a material at? What phases occur at that temperature? Those are CalFed type models, and so that's why it sort of forms the foundation of everything. The thermodynamic databases behind those are really kind of the genome of ICME in that sense. But you link those up with structure property models, right? You predict what phases are there and how big they are. We're getting into the kinetics now, the formation of things during precipitation. But you link the structure property side of things, like a strength model. How does the strength of a material relate back to its grain structure or the size and distribution of the precipitates? That's a structure property model. And then you link those to kind of performance, well, not just strength, but say life cycles of stress or something like that, an actual performance metric. All of that gets to kind of linked together in an integrated way. That's the I in ICME. The computational part is because we can do a lot of this in the computer. And yeah, no hate on Edison. He couldn't do these things in the computer. So we had to do a lot of perspiration and trial and error. We talk backwards in this sort of flippant way. Like they had to do things empirically because, they didn't have the ability to calculate these things. They weren't willy-nilly exploring all of the even numbers in a space, right? They knew through knowledge and history that, certain boundaries existed. But anyway, they didn't have the ability to do it in a computer. So that's the computational part of ICME. So you link across, and then you link across various length scales. Thermodynamics may tell you about the phases in a material that's kind of micro or nanoscale. But if you want to get down into the atomic scale of, like, say, cohesion at a grain boundary, you have to use different methods like DFT. And those are different methods of calculating process structure and structure property relationships. So you're doing it across the length scales, you're doing it across process structure, structure property, and you're doing it in this engineering way. I guess the E in ICME is engineering. You're really taking an engineering approach to performance, right? Not just a atomic structure because a phase's crystal structure is cool or something. You want to link that ultimately to performance. So that's been QuesTek's experience with ICME. It used to be called modeling and simulation, but we certainly started with the CalFad as the foundation approach. We certainly look at things from a mechanistic physics-based approach. Everything I was just rattling off is fundamental physics-based material science. That being said, we do understand the value of machine learning, AI type approaches to discern trends and maybe sift through data or ingest data that is ultimately made better or processed with physics-based models and such. We're getting into a whole nother tangent here. But that's ICME to QuesTek, right? And I think that's ICME to, I don't think how I just described it would be different from the way a lot of folks are using it and practicing it. But yeah, the difference these days is people can do the computation much better than ever before, and they can link it across length scales. And I don't just mean dumping a CSV and reading it into another software. You can kind of add software linked in this way. I'll talk more about QuesTek and our software initiatives these days later. But it can happen, and students themselves are taught computational material science even at the undergrad level. And I'm old enough to remember that it was computation was still sort of this different thing that certain material scientists were doing and wasn't really found its way into the mainstream material science community. Yeah.
So I get this impression that ICME is really, just from experience, I've seen these conferences, it's really aimed at metals. Is that, is it broader? Clearly it can be broader than that, but is actually finding application beyond just metals and alloys?
Well, yeah, absolutely. And QuesTek's done ceramics. It's some of the same thermodynamic databases can predict ceramics and phase stability in ceramics. And then you can come up with models of a ceramic's strength or hardness or toughness based on those phases. And so ceramics we've done for sure. Composites materials, which you've got a ceramic interacting with a metal or something like that. Full-blown polymer ICME is happening. It's starting to kind of get some legs. There was a center that Greg Olson has managed. It's still ongoing with Northwestern and University of Chicago and Argonne called SHIMAD, the Center for
I came out and gave a talk.
Yeah, I think good. Yeah, Center for Hierarchical Materials Design. So I don't want to Juan DePablo down at University of Chicago is looking at how do you build up the genomic databases and take a ICME type approach to polymer design. So it's possible. QuesTek did a project on bubblegum for Wrigley going back
No way.
20 years or something. So ICME and materials design can be applied to things other than metals, but absolutely QuesTek has focused a lot on the metals and more and on the hard materials side, ceramics, metal matrix composites.
Okay, so we've heard a brief history of how aviation materials have evolved. You've given us a description of what exactly ICME is. It's essentially sounds like, the cynic in me would say like, well, that's just like material science, right? As a discipline, we've been studying structure, property, processing relationships. But I think what has changed is the tools have evolved pretty wildly.
Right.
And this idea of doing it across length scales, not just picking a single relationship, but picking all of them that lead to the development of new material, that's a bigger bite than just what, our material science friends from 80 years ago were doing.
Right.
So I think I understand a little bit about ICME now. Could you tell us how this is actually changing aviation materials today in the modern era?
Well, thank you. Good segue to what QuesTek's been doing in the modern era in the last 20 plus years. We've been designing steels for aviation. So I can talk about some of those examples of some of our Farium steel design examples and maybe some non-steel examples, a nickel superalloy if we can get to that.
Absolutely.
But yeah, we QuesTek historically have done a lot of engagement type work for government clients, for corporate clients. So I'll talk more about the government stuff because I can talk about that freely. And these are some of our sort of banner success stories that you hear about or see on our website. But we've done a number of steel designs at QuesTek. We call them Farium. That's one of our trademarks. And there's a couple of varieties of Farium out there. I'll start with M54. Farium M54 is a steel design that we did for the U.S. Navy. This was funded by U.S. Navy Small Business Innovation Research type funding. They were looking for a very high strength and toughness steel that would be an alternative to what is essentially a single source steel out there that's used, and looking for solutions that would minimize the amount of cobalt, right? So they had these were the kind of performance things. These are economics, right? Thing has to be cheap. It's got to have high strength and toughness. But another dimension that concerned them was stress, corrosion, cracking resistance. If you get to this level of super high strength steels, you start to have issues of with hydrogen embrittlement and stress, corrosion, cracking, particularly right in the Navy environments, in saltwater environments on an aircraft carrier. So they were looking for this kind of a steel. They defined the requirements: high strength, high toughness, high stress, corrosion, cracking resistance, and minimal cobalt, like low cost. And that's where the QuesTek design of M54 came into play. And you can read about the design of the steel, and you can even see that we ended up making it into components. QuesTek coordinated the delivery of 60 of these hook shanks, which are the stick that catches the cable on the aircraft carrier when the jet lands. So this has been a great success story. But in terms of the technical, the real ICME, if you will, came into play, the stress, corrosion, cracking resistance, right? In these very high strength steels, they fail in the presence of hydrogen and they fail intergranularly. And you can see that plain as day on the fracture surfaces. So the grain boundaries are the weak link in the presence of hydrogen, the cohesion of the grain boundaries. So what can we do? We can look at elements that would improve the cohesion of those grain boundaries, and we can add those to the steel. And we can do it judiciously, not just throw in a dash, right? But we do it in a CalFAD context. So in this case, we did a bunch of DFT calculations, like ab initio, first principles stuff, looking at the impact of elemental additions to the cohesion of the grain boundaries in these types of steels. And we found that tungsten is the secret sauce, that when you add it to a steel, and it will segregate to the grain boundaries, and it will improve the cohesion of the grain boundaries significantly. So when you add it and you heat treat it in a way that it can get to the grain boundaries, you can greatly improve the stress, corrosion, cracking resistance, and that's shown in the fracture surfaces. If you take this M54 steel and you test it in a hydrogen environment, it's no longer intergranular, right? So So there's still another weak link out there, but it's no longer the cohesion of the grain boundaries. So that was
So
the
can I ask,
ICME.
like, how did you know? How did the ICME process tell you to try tungsten? What was the sort
Well,
of
we were looking
tool
at
that
which
suggested
elements,
that?
just in a general sense, which elements would segregate to a grain boundary. Would it be energetically favorable? And when they get there, do they improve or decrease the grain boundary cohesion? And those calculations were done across the entire periodic table, kind of in a model setup kind of way. And that pointed directly to tungsten being the one that could work. But then you got to turn it over to the thermodynamics. Okay, now if we're adding tungsten to this steel, starting without it, and you add it to the
Phases might show
steel,
up.
is it going to be free to roam, right? Will it be gobbled up into the carbides, where it's going to compete with chrome and molybdenum to form those carbides, which are already in the steel, or is there going to be a certain amount of it free in the matrix to roam? So so you have to do that, right? And when you find that there's some that's free to roam, that it roam, during heat, then you got to look at the heat treatment. Okay, if we use a tempering temperature at this sort of a range, would the tungsten travel enough distance, right? It's a big, heavy element. Yes. Okay, good. And let's put it into the steel with that sort of a level, and it segregates to the boundary, and then the proof's in the pudding. The fracture surfaces are no longer intergranular. So that's how we learned it would be tungsten. I think actually the better candidate from an energetics point of view would be rhenium, but that's much, much more expensive, right?
Yeah.
So you can survey the landscape with these initial calculations, and then you got to kind of hone in on things and across the length scales with CalFAD and with some of the kinetic calculations about diffusion distances. So the steel works, and that's why they made the components out of it, and it does have the strength and the toughness. And by the way, the low cobalt, that was another constraint, and the improved stress corrosion cracking resistance. But hopefully I'm kind of articulating how a number of different ICME type models were kind of looking at things simultaneously as we did that alloy design.
Yeah, that makes a lot of sense.
Yeah.
One question I have, so I have some experience working with some of the ceramic side of some of these thermodynamic modeling softwares, and one of the issues that we ran into was, for some systems there isn't data in some of these databases, and especially when you're trying to solve maybe a new problem or incorporate a new element or design an alloy that hasn't been around before, you might not have a lot of data to be able to perform some of these thermodynamic calculations. So what was the approach there? Would it be to actually generate this data, or to maybe find workarounds of solving these problems without it?
First of all, I think some of the thermodynamics databases for certain ceramic systems have evolved quite a bit, and there are oxide thermodynamic databases that you can use. But ceramics are complicated, and especially the multi-component space. But in general, when you're trying to develop a new thermodynamic databases, you're going in there and you're studying the various binary phase diagrams and binary heat capacities and stuff, and ternary heat capacities. The brilliance of the CalFAD method is essentially that. Like, once you nail things down through binary and ternary level, you can extrapolate to these fourth and fifth order type terms with relative confidence, because those kind of out terms of quinternary type interactions are very minimal on the overall energy. So I'm not a thermodynamic person, but if you got to start from scratch, then you look for the binaries and the ternaries, and you build out from there until you run into strange phases that weren't necessarily predicted, and then you got to adapt your databases. But that's been an iteration, and I think the modern status of databases for oxide systems is quite advanced.
In my case, I was actually more on the I was looking at ceramic interactions with various actinide species, which are not necessarily as populated.
Yeah.
Or if they are, there are sufficient protections on them that you can't always access them.
Right. Yeah. So even some of the metallic databases, I don't know if they have all the the actinides and the full spread of elements. Some of them do, but not to if you really want to design with an actinide carbide or something. But the question of is it just, do we have to go out there? No, there are some, and Taylor, this realm, there are ways to calculate energies of compounds and stuff at 0 degrees Kelvin, right? That sort of form the baseline enthalpy parameters that would feed into new databases. So there are efforts, I know, to build up these databases using first principles or computational methods without having to build out ternaries. filling in the sort of missing gap of 0 Kelvin energies, mixing energies and enthalpies and things. So I know there is in AI space and stuff, an effort to build up these databases even more rapidly.
Well, I will never see an airplane take off or land on an aircraft carrier the same without thinking about this hook you guys made.
Yeah.
I think that's pretty awesome.
Yeah.
What else have you worked on?
Another example would be a nickel superalloy that we designed, single crystal nickel alloy design, and we're talking about the blades of turbine jet engines now. And for jet engines, right, for propulsion engines, the technology moved from nickel superalloys to directionally solidified to now single crystals. They've been looking at, and those are the ultimate in creep performance and stuff, if you can get the blade to be a single crystal without any grain boundaries. When you want to scale up that sort of technology to industrial gas turbine engines, the blades are much larger, right? The blades in a jet engine are like the size of a pack of cards, and these IGT blades are the size of a loaf of bread, huge. And it's a huge challenge to cast something that much larger as a single crystal. So that was the challenge statement from the Department of Energy. Can we get single crystal nickel alloys that have that could for industrial gas turbine IGT engines that have the that take advantage of some of this single crystal technology that aeroturbines were doing?
I've got a stupid question for you. I should know this. Yeah. But every time I hear cast single crystal, my brain is like, what? How do you do that? Because you cast something, you're going to nucleate all over the sides of the mold, and I should know the answer to this, but are you casting it and then you're doing like a slow solidification, like a Bridgman process to turn it into a single crystal?
That's how they do it with these molds. And I'm not an expert, and there's a lot of like secret proprietary sauce, but they start with a little seed, which is like a ground 100 nickel surface or nickel surface, and they put that in a certain location in an investment mold. And then through a process of keeping it superheated and then slowly cooling it from bottom to top, they can make this whole casting in a complex shape now into a single crystal. But it is amazing. And I've been to the places, and you can't really see how it's happening. And I'd really like to know more about it. But yes, and they do it with all these internal channels, right? Cooling channels and stuff too. And it's already a complex blade shape, but it's got all this internal structure. Pretty amazing. But scaling that up, like, and maintaining the single crystalness, right, during that sort of a process is a huge challenge. And the freckles are the things that develop. You can do that as carefully as you want, but these weird convective instabilities can develop that sends like different versions of the liquid in different directions, and then you end up with essentially a grain boundary, right? No longer a single crystal.
Interesting.
Right, and that is definitely related to the density of the liquid as it solidifies, right? It starts as a dense molten nickel superalloy. But when you want to add these elements, like rhenium is often added to these alloys for creep resistance. But that exacerbates the solidification issue. As the material solidifies, the first to solidify is rhenium rich. It leaves the remaining liquid much less dense, and then you can have regions of high density liquid, low density liquid, and you get this sloshing convective instability, I guess, that breaks up the single crystal process. So it's really hard to kind of maintain this all and do it in a way such that you can make the blades much larger. So that's the challenge. How do you limit those liquid density differences during solidification? That's a thermodynamic calculation. You're calculating the density of the liquid as you fall along the liquidus curve, right? And how can you do it with minimum amount of those elements? Well, you could do it with 0 of those elements, but you're going to still need a certain amount of those heavy elements like rhenium for eventually the creep resistance. So this is what we did. This was the design challenge. How do you minimize the liquid density differences during solidification, but maintain enough rhenium in the system such that you get the good gamma prime microstructure in the end, and it's highly creep resistance, et cetera, all while making something that's eventually homogenizable. It kind of goes through some heat treatment steps. That was the main trade-off there. So we designed a 1% rhenium alloy that has the creep resistance of the like 3 to 6% rhenium alloys, but essentially has the castability of a 0% rhenium alloy. And all of that was done in, computationally, ICME. In fact, this was done with multiple databases. Certain thermodynamic databases are used to predict the the liquid density differences during solidification. Other thermodynamic databases are used to predict the gamma prime composition and phase fractions, only because different databases work different for different parts of the problem. And that's sort of the integration of the ICME type side of things. So yeah, we designed an alloy, patented it, and it's castable at large scale. We actually worked with one of these foundries to produce a large scale blade with an OEM's mold, so it works. And it's got the creep resistance of a 3 to 6% rhenium alloy, and that's a huge, big deal. And because rhenium is thousands of dollars an ounce or something. So
it's a showstopper.
Right. So from going from 6% rhenium to 1% rhenium, the number of pounds that would equate to in a large scale IGT gas turbine, it's a huge cost savings. So I went through that pretty quickly. I usually do it with a whiteboard in front of me or something, but hopefully you can appreciate there are different length scales of modeling happening there. They're interplaying with one another. The outputs of one thing are going into the inputs of another. We're doing it with different databases and different parts of the calculation chain, right? That we got to add that all together and do it in multi-component 8-element space to do these alloy designs.
Yeah. We just did an episode on nickel superalloys, episode 70, if you want to go back and listen to it. But I think it was really great at describing how these gamma prime, precipitates lead to the strengthening, which is so critical in those materials. I'm curious, where you guys were trying to tweak the composition of the overall material such that you avoid these gradients in the casting process.
Yeah.
This is now a multi-objective problem where you still need to preserve the precipitates and they have to do their job, but now you have this additional constraint. What did you run into instances where, in order to get the right, density matching, that it would have negatively impacted the precipitates, or did you just get lucky and it happened to work for both?
No, it's a trade-off. That is a trade-off, right? If you add more rhenium to the system, you're going to get more precipitates, but you're going to get worse castability, worse or larger liquid density differences. So you got to kind of find that sweet spot. It's not just a linear trade-off of like a hatch pattern, a sweep, right? These are you got to look at a contour plot of those quantities as a function of, and show really where are you going down the valley this way, but only slightly along the ridge line of the other property. That would be ideal. So you're moving from one place to another while one property is maintained, but another one is maximized. So but that's fundamentally the trade-off. And you do have to have some rhenium in there. And I might even have it wrong. Rhenium actually, I think, segregates to the matrix. It's right. It doesn't add to the phase fraction, but I think it goes to the matrix, and thus, it gates the eventual coarsening of the precipitates, and so it slows everything down that way. The coarsening, right, which ultimately related to the creep resistance over a long time. Anyway, maybe I've got it right, maybe I got it wrong, but in any case, yes, it's a multi-objective thing across length scales. There needs to be a human operator that's saying, like, hold on a minute, that doesn't make sense. Sometimes, right? Maybe not for this particular example. Like, hold on, I must have something wrong here. This trend is looking to be in the opposite direction. But in any case, that's what QuesTek does, and that alloy is another success. And it has been produced at scale and not yet found its way into an actual gas turbine. So for all you gas turbine manufacturers out there, give me a call.
So you've described your ferrium for the hook. You've described now a nickel superalloy for the engine, obviously. Other examples you want to talk about?
I think I'd like to talk a little about the kind of the next frontier now. I think because I think without getting too much into more QuesTek examples, this idea of alloy concurrency. This is the exciting part. I've just described how QuesTek and in general how ICME alloy design has evolved and how we've been practicing it. The next frontier is concurrency. This is happening now. And that's not just designed to a set of property performance requirements. I want an alloy that's this strong, this tough, this stress corrosion cracking resistance. It's kind of merging the design of a component, the actual design of a component with the design of new materials. Concurrency in engineering, that's already been achieved across the other disciplines. They're designing the mechanical engineering of your iPhone at the same time they're considering the electrical engineering of the enclosure and stuff. But only recently, at Apple included, right, have they also kind of brought materials to that table. And so materials design at the same time that you're doing component design, that's concurrency, right? And that's only possible if you have alloy design, if you've got the ability to computationally and rapidly design new alloys. So that's kind of why it's the final frontier. I can talk about some industrial examples in this theme. Apple is an awesome company. They're very materials forward. There's even a QuesTek connection that Jim Yurko acknowledged at the 2022 TMS talk that he gave. But in any case, Apple is a company that looks at new materials as they're starting to design new devices. The Apple Watch was an example of that. You can look up the patents. They designed a new aluminum alloy, a new gold alloy, a new stainless steel alloy for the Milanese loop bands. They designed these materials at the same time they were doing the design of this new product. It all kind of came together. These days, it's titanium, right? They're touting the new usage of titanium. It's Ti-64, but no doubt it's a probably custom tweaked version that they've developed for their particular application and needs. That's concurrency. Another good example, SpaceX Tesla. And there's a QuesTek lineage there too, Charlie Cumin, but more on that later. But they're doing awesome things at new alloy design and concurrency. I know everyone knows the example of the gigacasting, the large-scale castings that Tesla's using. You can look up the patent. They had to design a new aluminum alloy for that application. Not just these huge presses that are, my God, they're huge house and all the engineering that goes into that. But they needed to get it out. That the alloys out there that existed didn't work. They didn't have that combination of fluidity, thermal conductivity, and solidification characteristics. And ultimately properties in the as-cast state, right? They didn't want to have to heat treat these big castings. So they designed a new alloy that would meet the job. So they were doing this at the same time as they were like kind of designing this notion of a gigacasting. So materials concurrency, it's awesome. And it's enabled by materials design. You can say, boy, this component would work a lot better if the properties of the material here in this little corner were these properties. Right. And normally someone would say, well, we can't get that, so just make it thicker there. But no, if you could actually say, well, what that would mean taking this existing material and tweaking it in a way that it gets to those sort of properties, not necessarily even tweaking an existing, designing a new material with those particular properties. That's concurrency. So the example at QuesTek we're excited about is some of the work we've done on ARPA, an ARPA-E, Department of Energy, Advanced Research Projects Agency Energy, a program on the design of niobium alloys for turbine engine applications. So this is the ARPA-E Ultimate program. And Taylor, I think you've been connected to some of this effort out of ARPA-E.
Yeah, we know that one well.
Yeah. So this is concurrency too. We worked with Pratt & Whitney as the partner to say what would really a niobium alloy need to do. What kind of properties would it need to have in the case of a turbine blade, in the core of a turbine blade? Because we knew from the beginning that, regular niobium is not going to cut it. Regular niobium, even C103, does not have says horrible oxidation resistance. So you have to have a core niobium alloy that has creep resistance, and you have to grade that into a case niobium alloy. It's closer to a high entropy alloy, by the way, that has the oxidation resistance. And the concurrency there is folks like Pratt & Whitney telling us, well, yeah, you can, it's not just about 100-degree bump in operating temperature. It's really going to mean these particular increases in the metrics of, say, creep resistance or stresses and strains and that sort of thing, telling you what the actual requirements of a component of this sort would be, and then designing the material to match those requirements. So and that's a very complicated material, right? One niobium alloy in the core graded to a case niobium alloy in the case. You need to make sure that case alloy is then compatible with a bond coat and a coating. The whole thing is a very multi-scale ICME intensive exercise. And we've made some progress there. That program's moving to a second phase. It'll be a while before niobium alloys are spinning in turbine engines, but this would be a huge big deal for energy efficiency. It's a cool program to be involved with. The government is really kind of looking to the next frontier, because making jet engines that burn hotter would save just tremendous. They used to throw out these metrics. I should have them at the tip of my tongue, but a 100-degree increase in operating temperature.
It's colossal, yeah.
It would be like getting rid of half of the cars or something, or something like that. But in terms of, anyway,
Yeah.
huge foresight, and we'll get there eventually. But it's definitely an exercise it's not for empiricism or accidental discovery, right? It's for ICME, computational design, and it's for concurrency. This particular alloy, right, has to be printed. The graded, or this solution would need to be printed to get the graded from core to case. And so it has to be processable into a powder, and it has to be printable by directed energy deposition, all these constraints that you need to consider up front. That's also what we mean by concurrency.
So Jason, I'm kind of curious if we have lots of listeners in all sorts of different spaces. If they're hearing an episode like this and they're like, this sounds like exactly the challenge that I face at my company. You guys offer tools and a package of tools that people can sort of utilize to address their own challenges, right? You want to talk about some of those?
Thanks. Shameless plug time. But no, this is awesome. I've talked about these QuesTek stories and histories. That's the history of QuesTek, the engagements and the alloys that we've designed. But we're currently going through a digital transformation ourselves, a pivot to a digital company. We're putting together all the tools and models that we developed over 20 plus years, nearly 25 years, into a package that folks can use. ICMD, and it stands for Integrated Computational Materials Design. So a combination of ICME plus materials by design. A lot of the models I just talked about, grain boundary cohesion, phase stability, and strength models across various alloy systems are part of this package. So folks can do what I'm describing. And I'm excited about that. We've done a lot of successful things ourselves. We've helped companies do successful things. But now I think the workforce has matured certainly to a point with the knowledge and familiarity with computational material science that this is a product that a lot of people can use. We talk about the democratization of ICME. This tool allows folks to do quick models. You don't need to know the physics of Orwan looping, strengthening. You just want to be able to predict the strength of a precipitation strengthened alloy. So we're excited about it. It's called ICMD. Check it out. It hit the street at the end of last year, or rather 2022. 2023, it started its market adoption. There's some press releases around early adopters like Daido Steel in Japan on QuesTek's website.
Oh, cool.
Yeah. So, but we also still do the engagements and the services, and there's a lot of ways in which ICMD can be customized, or we can work to have it integrated within a client system or use a client's models. It's all very modular that way. And so, that's kind of the final frontier. This is what will enable more than just a few companies out there, but all of the companies out there to do alloy design and materials concurrency.
That's awesome. So we will put a link to this in our show notes if people are interested. Jason, this has been a hoot to chat with you. The future is bright for materials design. It's very exciting to see more and more tools coming online that can just really deal with the stuff that we couldn't deal with in the past, that was too complicated, too multi-objective, too many parameters to sort of consider, too many length scales to consider. The fact that we're coming up with tools that can bridge those challenges is just a really exciting time to be doing material science.
Yeah, getting them to talk to each other was always one of the biggest things, right? You could buy all these softwares, but then you had your sort of discrete experts in each of them,
right.
And rarely did they talk to each other. And if they did, it was oftentimes hard to bridge that gap and communicate across that. So seeing that become more centralized and become more accessible so that new problems can be solved with it is really cool.
Okay, Jason. It's been a blast.
Yeah, thank you. It's been my pleasure. I've been a fan person for a long time, so this is super cool. And you guys keep it up, and go materialism.
Thanks so much. Yeah. Okay, we'll talk to you later.
Bye-bye.
This episode of Materialism Podcast is brought to you by QuesTek's ICMD software. ICMD is a new materials design and engineering platform that captures the power of integrated computational materials engineering, or ICME, in a cloud-based software-as-a-service offering. ICMD helps innovative organizations design, develop, and deploy novel materials at record speed. The software is built on computational models developed by QuesTek to deliver hundreds of material science engagements completed on behalf of NASA, SpaceX, Apple, and many more. With ICMD, materials engineers can see how a wide range of variables will impact a material's structure and properties, such as strength, toughness, corrosion resistance, and fatigue. Or you can start with the performance that is required and then identify the composition and processes that will help you achieve it. To try ICMD and see what innovations it can unlock for your organization, you can visit QuesTek.com. That's QuesTek.com.
This episode is sponsored by California Nanotechnologies, or Cal Nano. If you've listened to the podcast, you know that we are big fans of them. We've done a couple episodes with them, and I, as a professor, have used their services multiple times over the course of my career. They have some really great services. They've helped us with spark plasma sintering at an extremely large scale, way bigger than what you're thinking. They can make some huge components. I've always had great success with them. They turn out high density, quality parts, to order, and pretty quick turnaround. And they also have some other capabilities, including cryo milling. Check out our episode on that. We think that they're an awesome company, and we're proud to stand by them as a sponsor of the show. The Materialism podcast is also sponsored by Materials Today. Visit materialstoday.com to stay up to date on the latest happenings in the material science field and read some fantastic articles they have published. You can head over to elsevier.com to find out more about their journals, books, conferences, and related programs. Okay, thank you for listening to this episode. It was super fun to have you along. And as always, we would love to hear feedback from you. So check us out on Instagram. We are at the @materialism.podcast handle, or you can send us an email, materialism.podcast@gmail.com. And if you want to do me a huge favor, I would love it if you gave us a review. We are tantalizingly close to stealing that #1 spot in the chemistry category. Nothing would make me happier than to have a material science podcast in the #1 spot of our chemistry homies. So help make this happen. A review, share it with some buddies. That would just be super rad. As always, we're grateful to the people that make the music for this. That's Alphabot and Kolobyte. They make some cool stuff. Check them out, and we'll see you next time.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.